Section 5.3 is about logarithmic functions. Logarithmic functions are basically inverses of exponential functions. So they equate to each other like this. Whatever the base of the log is the base of your function. Whatever the x is your answer. And whatever the y is the exponent. So when you see something like this, what we're basically asking you is what power do you need to raise 2 to in order to make it 8? And the answer is just 3. Or if you wanted to write that in exponential form, 2 to the third equals 8. These both say the same thing, just in different forms. Right, similarly here, we're asking what you need to raise 8 to make it 64, which is just 2. And again, if I wanted to write that in exponential form, 8 squared equals 64. The last one, a little bit different. These two I have a number here. This one I don't, and that's going to occur in two cases. The first is the one you see above, log, and whenever you don't see a number there, there's an invisible 10, and we call that the common log, or log base 10. The other case you're going to see is ln, which is equal to log base e. There's that little Euler's number again, and we call that the natural log. But in this case, we have nothing there, so it's a 10. So we're asking what you need to raise 10 to in order to make it 1. And the answer to that is 0, or in exponential form, 10 to the 0 equals 1. And again, it means exactly the same thing. They're just written in different forms. Now, these were fairly simple, but you get to some harder ones. So on the first one, log base 5 of 1 over 625. And I can look at that and say, -4. You probably can't. If the numbers get worse, like a little bit harder like this, we can use something called the change of base form. Now if you look at your calculator, you're going to see two log buttons, a common log and a natural log, but unfortunately no log base 5. So what I'm going to do is use a formula so that I can express log base 5 as one of these logs. And the formula for that, in this particular case, is natural log 1 over 625 over the natural log of 5. And if I plug that into my calculator, I will get -4. Okay, just remember, the number out here goes on top. The base always goes on the bottom. And if you don't like natural logs for some reason, you can also use common logs. And they will give you the exact same answer. Now the natural log of 5 and the common log of 5 aren't the same number, but the ratio of these two is exactly the same. So let's try that with this one. Log base 2, 10. I'll take the natural log of 10 divided by the natural log of 2, and just remember, the base always goes on the bottom. Plug that into my calculator, and I get approximately 3.322. And let's try the same thing on these. If I use the change of base formula on this, and I'm just putting it in like you would put it in your calculator, you would get out the number 3. If I did the same thing on this one, and let's take a brief second to look at this again. Unless you go into the math function and root around a bit, you are not going to find a fourth root button on your calculator. You're just going to have the standard square root available to you. An easy way to do roots is raise them to the 1 over whatever index we have. So the 5 goes here, that's the exponent key, and instead of the 4, it's 1/4. So the fourth root of 5 is the same as 5 raised to the 1/4 power. So instead of trying to write this, I'm just writing this as 5 to the 1/4 power. They mean exactly the same thing. But if I plug this into my calculator, I would get out 0.25. And since we really don't like 0.25s in this section, just hit the math frac button and get back to 1/4. So change of base formula will work here, but there's another rule they're trying to get you to understand here. And that is when the base of the logarithm and the base of this exponential equation are the same, or exponential expression, they cancel out, and we just drop down the exponent. So in other words, on this one, that's actually 5 to the 1/4. The two bases are the same, they basically cancel out, and the 1/4 just drops down as your answer. Okay, next up, we have to do some basic graphing of logarithms, and we're not going to do a whole lot of detailed graphing, just some basic graphing, just like we did with exponential equations. So your basic logarithmic equation goes to the point 1, 0 and looks kind of like this, which you would expect. Since it's the inverse of exponentials, you'd expect it to be symmetric around the line y equals x, and the exponential equation would look something like that. So they are symmetric around the line y equals x. And just like you know about inverses, domains and ranges shift. So the domain on your logarithmic equation is 0 to infinity, excluding the 0. Range is negative infinity to infinity, or all the y's. And we have a vertical asymptote at y equals 0. So that's the basic shape and domain and range of a logarithmic equation. And then you're going to start graphing things that look like this. So just like we did with exponential, if you're graphing on the MyLab system, pick the general logarithmic equation shape. If not, we'll just plug it into the calculator when we're done. All you really need to know are where the shifts are. So the horizontal shift comes from there. And that's going to be a shift 2 to the left. Let's see, then we have a stretch by a factor of 3. So we have a vertical stretch by 3. We have an x-axis reflection and a y-axis reflection. And finally, we have a vertical shift from that one. All right, so we have all our shifts. So I'm going to plug this in my calculator, and when I do, I get something that looks kind of like this. My vertical asymptote shifted to 2, goes down kind of in that direction, and the important things to you are the domain of all reals and the range. Sorry, range is all reals. The domain is negative infinity to 2. And that's really as specific as you're going to have to get. Now, here's the thing that causes problems on almost every single final exam. If you look at this graph I have, it looks like it's moved over 2 to the right. And up here I said a horizontal shift 2 to the left. Well, what usually happens on the final is everyone plugs this in their calculator, gets the picture, gets these parts, and then says horizontal shift 2 to the right, and then they get that part wrong. What's happening here is we had the horizontal shift 2 to the left, but then the y-axis reflection flipped it back around. So when you're going through this part, listing your shifts, go by the numbers up here, not what you see on the calculator screen. And the last thing you have to do in this section is do some word problems. So here we have the number of decibels given by this formula, and I sub 0 is 10 to the negative 12th, and we're given a sound of intensity 5 times 2 times 10 to the negative 6th, and you want to know what the decibel rating is. All you have to do on this type of problem is plug it directly into your calculator. So in your calculator, just plug that in. And you'll note, since I don't have any leading number here, like a 5.2, I'm writing it as 10 raised to the negative 12th power. But for this one, 5.2 times 10 to the negative 6th, I'm using that little e. That little e is right here above the comma. So hit second function and the comma, and you'll get this number right here. And plug that in your calculator, and you should get approximately 67.2 decibels.